Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python, Part 7. In this lecture, we are going to discuss TD Lambda as a generalization of the n-step method. Lambda is a parameter that is associated with a vector called the eligibility trace, which we'll be learning about in this lecture. You may have noticed that the code for the n-step method was pretty complicated. In particular, it's not so straightforward to keep track of the last n rewards all the time. Lambda allows us to use a more elegant method of choosing a trade-off between TD0 and Monte Carlo. In particular, we won't have to keep track of the last n steps, and we'll be able to make updates without having to wait n steps, and instead just wait one step like in TD0. We'll see that lambda equals 1 corresponds to Monte Carlo, lambda equals 0 corresponds to TD0, and any lambda in between is a trade-off between the two. So first, let's further generalize the n-step method. Remember that we can define different g's depending on how many r's they depend on. A strange idea might be to form a return that is a combination of these g's. For example, 1/2 g1 plus 1/2 g2. Now, to take that strangeness to the next level, consider that we can sum up any number of g's, even an infinite amount of g's. The only requirement is that the weightings for each g have to sum to 1, since the final g must be on the same scale as the original g's. For the TD lambda method, the lambdas are given very specific values. In particular, they decrease geometrically. And now if you notice, these don't sum to 1, since the first weight is already 1. So they would need to be normalized. In particular, we are interested in normalizing this for the case where n is infinity. From calculus, we know that the sum of these lambdas is 1 over 1 minus lambda, and so we should scale the sum of returns by 1 minus lambda. We call this the lambda return. You may want to pause the video to write this down on paper to convince yourself it's true. Once we have our lambda return, we can assume our episode is going to end at some point. Let's call that time step capital T. Because we're counting from n equals 1 to infinity, when n reaches capital T minus lowercase t, the n-step return is really just the full sampled return g of t with no superscript. So we can manipulate the lambda return to separate the shorter n-step returns and the full sampled returns. We can manipulate the second term until we're left only with the part that depends on n inside the sum. Now the next step is, if you manipulate some of the identities related to series, you can solve for the second sum in closed form. So now we have an expression for the lambda return in terms of all the n-step returns that go up to the end of an episode and then the full return. Pause the video if you want to understand this derivation. I would recommend walking through it using a pen and paper. What you should notice about this equation is that when lambda is 0, we get the one-step return, since 0 to the power 0 is 1. This is TD0. When lambda is 1, the first term is just 0, and so we get the full return, which is the Monte Carlo method. Any lambda in between will give you a combination of all the n-step returns with a geometrically decreasing weight. At this point, the obvious question is, this seems worse than both Monte Carlo and the n-step method in terms of computational effort. With Monte Carlo, all we need to do is compute the returns for the episode. With the n-step method, we have to compute the n-step return for every time step. But now we have to compute the Monte Carlo return and all the n-step returns from n equals 1 all the way to the length of the episode. This sounds like a lot more work for what is not clearly a benefit. Now the next step requires some mathematical wizardry, which is definitely outside the scope of this course, so no proof will be given. However, this method has been around for some time, so you should have no problem searching for papers that discuss it. This algorithm we're about to look at is in fact only an approximation to using the true lambda return that we just talked about. We of course don't actually want to use the true lambda return in any practical scenario, because that would mean calculating all the different n-step returns and the full return. First, let's recall what our parameter updates look like when we're doing TD0. We have our target, which is r plus gamma times v at the next state. We have our prediction, which is v of s. And we have the difference, which is the subtraction of those two. This delta is called the TD error. This helps us tighten up the notation a little bit, but this is still just plain gradient descent. To implement TD lambda, we need to introduce the idea of the eligibility trace. The eligibility trace is a vector the same size as our parameter vector theta. Essentially, it keeps track of our old gradients much like momentum in deep learning. We define the first eligibility trace as 0, and then every subsequent eligibility vector will be the current gradient plus a fraction of the old eligibility vector. This fraction is just gamma times lambda. Basically, lambda just tells us how much of the past we want to take into account. We can then redefine the parameter update step to use the eligibility vector rather than just the gradient. Recall that momentum in deep learning works very similarly. We keep a velocity vector, which is the sum of the most recent gradient and part of the old velocity. Then we update theta to go in this direction, like how r theta goes in the direction of the eligibility vector. Notice how, because the update for theta now only depends on the next state, we can do our updates at the next step rather than waiting n steps like in the n-step method. But also remember that this is just an approximation to using the true lambda return. One distinction that is made sometimes, because the n-step method and true lambda return require looking ahead to later states, we call this the forward view. Whereas TD lambda, we update our current theta based on past errors, so we call this the backward view.